Hey, I'm back. So I'll be going over LeetGPU problems again. So today we are going over two easy problems actually. So both are pretty much the same. They just change with the requirements. But I would say it didn't take me that long to implement it. I actually got it one shot. Um, and it doesn't really need any explanations for it, even for the parallel algorithm. Even the naive is pretty fast. I don't think there's like a lot of opportunities for optimization techniques here, but I'm working through the medium problems right now. So I should have some more videos on loop unrolling and algorithm cascading and other techniques soon. So until then, uh, I'll be going over these easy problems. So I picked this ReLU because it's an activation function, so it's important for any machine learning thing that we do. So they give us an array. Basically, they tell us it's a vector, but it's pretty much an array of 32-bit floating point numbers. And they want us to apply the ReLU function or rectify linear unit. So ReLU is basically just this, even in programmatically, it's just this function, built-in function. If let's say if our x is something positive, it'll remain the same. If it's 4, it'll be 4. And but if our x is something negative, like -4, it'll become 0. So it'll basically kill all negative values. Um, so it's pretty much just like vector sum, but instead of summing the corresponding elements, we just apply the function and store the corresponding activation in the output array. So let's calculate the global thread index. So I'll just call this TID, and it's just thread ID x.x plus log. So this I I don't know what I was doing. So we'll just have a conditional to ensure it's within bounds. So ID should be within n, and once we have that, we basically say the output at the corresponding index would be we have to apply the function. So we'll just call the built-in max function. We'll just write whatever is there. So and here it'll be just input ID. So essentially there's no need for memory coalescing or anything like that, because it is accessing elements across the x index. So the memory access should be aligned by default by whatever we are doing, unless we're doing it in a weird way. So this should be relatively optimized. So I'll just try running it to ensure that it works before I submit it. Huh. I see. So we're essentially passing mismatched data types. So this is integer and this is a float. So that shouldn't work. So we could just say 0.0f and it should run. Huh. Yeah, so the percentile is very inconsistent, so I'm just gonna leave it at that. But if I go again, it should submit faster, and the difference in performance from my previous submission is not that much. So I'll be moving on to the leaky ReLU. So this one is pretty simple too. So it's pretty much the same as what we did before. But as if it's positive, it'll remain the same. But if it's negative, we instead of killing it entirely, we multiply our input variable with a small constant, a positive constant. So in this case, it's just 0.01. So if it's -1, it'll be minus 0.01. If it's 10, it'll be 0.1, minus 0.1. So essentially, we'll have to do the same, but when we call it, we can't exactly call the max function for this. So we'll be using the ternary operator. So I'll be getting the global index again. So I'll just type it out. Once we have this, we just call the conditional and say if thread ID is less than n. And here we're gonna basically say that if or x, or let's say we can store it the x value here first to make it simpler. I don't want to type it again and again. And if the global memory is accessed too many times, it'll be much slower too. So I'll just store it with one single access and store it in a local register. So ours, it's a float, so I'll just store it as a float. So basically it's gonna say that if value is greater than 0, the value will remain the same. If not, we are gonna basically multiply our constant with it. So 0.01 f val. That's basically it. It should work, I think. Let's see. So so I actually forgot the operator here, so I'm just gonna run it again. And this fast, so I'm gonna submit it. Yeah, so that's not bad. But yeah, this is again inconsistent. We should probably start using the profiler for the videos, but it'll be just a pain to launch the kernel. So for each algorithm, so I haven't really decided how I'm gonna do this yet. So anyways, hey, sorry, I actually ended the video prematurely. I actually wanted to talk about something else before I ended the video. So there is something interesting that I discovered as I was solving this leaky ReLU problem. So as you can see, we can't really just use the max function and just end the problem. So we use a ternary operator here. So there is an interesting concept called warp divergence. So a warp divergence is basically when threads of the same warp basically go in different branches. So it can be bad for latency and throughput. So instead of to avoid this, we use a ternary operator here. So why does the ternary operator work better and if-else conditional work worse? So I used if-else conditional for my first implementation. So it was really bad. As you can see in the performance, the percentile is pretty inconsistent, but the performance is pretty consistent, I think. So I used the conditionals here. As you can see, the performance improvement in using the ternary operator was like more than half. So why exactly is that? So if-else conditionals are it can take you in branches, and ternary operators is branchless. It can be branchless at times, but here it is not it is branchless because it compiles into a predicated instruction. So I'll be getting over it in Paint. So I actually have to, yeah, so I'm on Paint now. So let's say we have a warp here. A warp was just 32 threads executing in parallel. So in this warp, we have in CUDA, we have a specific concept called SIMT. So SIMT is single instruction, multiple threads. So we issue a single instruction and we execute all of this in parallel within a warp. So that's what makes CUDA so powerful. So if you have if-else conditionals that branch, it basically the warp scheduler basically what it does is, so it basically starts with the if conditional, and it basically checks for all threads, and then so that's basically like let's say a half satisfies AF, then it'll run the else for the rest of the 16 threads. So as you can see, this is much slower. It has more latency and memory throughput. So to solve this, we basically use a ternary operator. So ternary operator basically makes compiles into a predicated instruction in CUDA. So that helps us a lot. But it is important to know that ternary operators can branch too. So yeah, I think I'll end it here.